Have you ever built a model that seems to perform perfectly until you realize it never actually learns to detect what matters most? That's what often happens when you train on imbalanced data. It's like trying to study rare diseases in a classroom where 99 out of 100 patients are healthy. The model looks accurate, but it misses the few cases that really matter. In this guide, we'll explore practical techniques to help your models become smarter, more reliable, and more fair, even when the data is stacked against them. To do that, we'll break the solution into 5 essential strategies, each tackling imbalance from a different perspective. Let's talk about it one by one. Data level methods. Adjust the dataset directly through oversampling or undersampling, giving the model a more balanced view before training begins. Algorithm level methods. Modify how the model learns by applying class weights, cost-sensitive loss, or ensemble methods, without changing the data. Evaluation metrics. Use smarter metrics like precision, recall, F1, or AUC to measure performance where it matters, not just overall accuracy. Advanced approaches. Apply cutting-edge techniques like GANs, meta-learning, or curriculum learning to tackle extreme or complex imbalance cases. Application scenarios. Real-world use cases like fraud detection, medical diagnosis, and rare event prediction, where imbalance is the rule, not the exception. Let's begin with data-level methods, the most intuitive way to deal with imbalanced datasets. Instead of changing the model, we change the data. These methods try to rebalance the dataset before training even begins, either by adding more samples to the minority class or by reducing the number of samples in the majority. Random oversampling is one of the simplest and most common methods to handle this. It works by duplicating existing samples from the minority class until the dataset becomes more balanced. Its main advantage lies in its simplicity and speed, making it ideal for structured datasets like tabular data, simple image classification, and basic text tasks. However, it may lead to overfitting, particularly if the minority class is very small. For time series, a window-based variation is preferred, as simple duplication can destroy temporal relationships. Random oversampling fits binary and multi-class classification tasks for tabular, image, and text data. SMOTE, synthetic minority oversampling technique, offers a smarter alternative by interpolating between real minority data points to create synthetic samples. This reduces overfitting compared to random duplication and enhances generalization. However, it may generate noisy samples near class boundaries and doesn't work well with high-dimensional or categorical data. It's best suited for numerical tabular data, especially when the minority class forms dense clusters. Similarly, ADASYN, adaptive synthetic sampling, focuses on generating synthetic data near hard-to-learn samples, those most prone to misclassification. While effective for complex boundaries, it may overfit noisy or ambiguous data. Both SMOTE and ADASYN are ideal for classification tasks involving structured numerical data, but are less applicable to image, text, or time series formats due to interpolation challenges. Borderline SMOTE takes targeted sampling even further by focusing solely on borderline minority samples, those near the decision boundary. This helps improve performance in high-risk misclassification zones, especially in medical or fraud detection cases. However, it's also more vulnerable to noise. Like its predecessors, it suits tabular data best. Meanwhile, random undersampling offers a simpler route by removing samples from the majority class. It's fast and efficient for large datasets, but may cause information loss. This method works well when you have an abundance of redundant data in the majority class, and the model can afford some pruning. It's most suitable for classification tasks on large, structured tabular datasets, but not for time series, images, or text. Atomic links cleans the decision boundary by identifying and removing close pairs of samples from opposite classes, especially the majority class, to clarify overlap and reduce ambiguity. Although useful, it's more of a boundary cleaning tool than a standalone balancing method. It works best when combined with other methods like SMOTE, forming hybrid strategies such as SMOTE plus Atomic links or SMOTE plus ENN, edited nearest neighbors. ENN removes noisy or mislabeled samples by checking each instance against its k nearest neighbors and discarding those that disagree with their local majority. While ENN enhances boundary clarity and model stability, it must be used with care due to potential overcleaning and slower computation on large datasets. Both methods are ideal for structured, numerical tabular data with noisy class boundaries. Near-miss is another intelligent undersampling technique that keeps only those majority samples closest to the minority class, helping sharpen the decision boundary. While effective, it can be computationally intensive. It suits numerical tabular data in classification contexts where boundary precision matters. Hybrid methods combine the strengths of oversampling and undersampling, such as SMOTE plus Atomic or SMOTE plus ENN, to balance data distribution while cleaning ambiguity. Though powerful, these methods require more tuning and domain knowledge. Finally, data augmentation creates new, realistic data via transformations rather than duplication. It's highly domain-specific and excels in images, flipping, rotating, text, paraphrasing, synonym replacement, and time series, jittering, warping. Poorly designed augmentations can mislead models, but when applied well, this method greatly enriches datasets across classification, detection, and generative tasks. With that, we conclude our exploration of data-level methods, setting the stage for algorithm-level methods that directly alter the learning process. When balancing the dataset isn't enough or isn't even possible, we turn to algorithm-level methods. These approaches don't alter the data directly, but instead modify how the model learns, giving more attention to underrepresented classes. One of the most effective techniques is class weighting, which adjusts the loss function to focus more on the minority class. This approach is easy to implement in frameworks like scikit-learn, TensorFlow, and PyTorch. However, in extreme imbalance scenarios, e.g. 1 to 1000, it might not be sufficient on its own. Class weighting is especially effective with cross-entropy loss and is widely used in neural networks, logistic regression, and SVMs. It's suitable across data types, tabular, image, text, and time series, and works for both binary and multi-class classification, including pixel-wise tasks like semantic segmentation. Cost-sensitive learning expands on class weighting by incorporating a custom cost matrix into the learning process. This allows the model to prioritize specific types of errors by penalizing them differently, reflecting real-world risks and consequences. Its biggest strength is flexibility, allowing tailored modeling in domains like medical diagnosis, finance, and cybersecurity, where the cost of false negatives or positives can be critical. However, designing an effective cost matrix requires domain expertise, which adds complexity. This method supports both classification and regression tasks, and it's applicable to all data types, as long as the model supports cost-based optimization. When adjusting a single model isn't enough, ensemble methods offer a more scalable approach. These methods combine multiple learners, often trained on resampled subsets, to improve decision-making on imbalanced data. Balanced random forest modifies the classic random forest by training each tree on a balanced sample, created through majority class undersampling. This ensures that every tree sees a fair distribution, improving the ensemble's ability to classify minority instances. Though powerful, it may extend training time and risk data loss on small datasets. It excels in structured classification problems, particularly with imbalance ratios like 1 to 10 or 1 to 20. Easy-Ensemble pushes this further by creating multiple balanced subsets from the majority class and combining each with the minority class to train separate learners. This results in a strong ensemble composed of weak learners trained on diverse views of the data. The trade-off is increased computational cost, but it's well suited for large-scale problems like fraud detection or rare disease classification. Similarly, bagging with resampling mixes classic bagging with either random oversampling, undersampling, or both. It's easy to implement and helps reduce variance, though less effective for small datasets or poorly sampled subsets. These ensemble strategies primarily target structured tabular data, though extensions to other domains are possible. Together, these algorithm-level and ensemble-based methods give us powerful tools to fight imbalance, not by modifying the dataset, but by teaching the model to care more about what matters. From simple class weighting to adaptive ensembles like Easy-Ensemble, the focus shifts from data to learning strategies. These techniques help ensure fairness, robustness, and better generalization, particularly in high-stakes scenarios. With our model training strategies in place, the next step is learning how to evaluate performance correctly. Because with imbalanced datasets, traditional accuracy is no longer a reliable measure. When working with imbalanced datasets, accuracy becomes misleading. A model might achieve 95% accuracy simply by predicting the majority class every time, yet completely fail to detect any instances of the minority class. That's why relying on accuracy alone can give a false sense of performance. To properly evaluate such models, we need metrics that highlight how well the model performs where it matters most, especially on the underrepresented class. Let's explore the most relevant and reliable metrics for imbalanced learning. Precision measures how many of the model's positive predictions were actually correct, essentially answering, out of all the times the model raised a flag, how often was it right? This is particularly important when false positives are costly, such as in spam filtering or fraud detection. In contrast, recall, also called sensitivity, captures how many of the actual positive cases the model successfully detected. It tells us how good is the model at catching real cases. High recall is critical in domains like medical diagnosis, where missing a true case could be dangerous. To balance the trade-off between precision and recall, we use the F1 score, which is the harmonic mean of both. F1 gives a single, balanced measure of a model's ability to avoid both false positives and false negatives, making it especially useful in skewed datasets. Beyond this, the ROC-AUC, Receiver Operating Characteristic, Area Under Curve, assesses how well the model distinguishes between positive and negative classes across various thresholds. With values ranging from 0.5 random to 1.0 perfect, ROC-AUC is valuable when you want to assess separability or experiment with decision thresholds. For situations with extreme imbalance, PRAUC, Precision Recall Area Under Curve, offers better insight than ROC-AUC as it focuses specifically on how precision changes with recall. It's ideal when the positive class is rare, such as in rare disease detection or anomaly detection. Another helpful metric is Cohen's kappa, which adjusts for chance agreement between actual and predicted labels. This provides a more realistic alternative to raw accuracy, especially in multi-class or noisy datasets where agreement by chance is non-trivial. Lastly, the Matthews Correlation Coefficient, MCC, is one of the most robust metrics available for imbalanced datasets. It incorporates all four components of the confusion matrix: true positives, true negatives, false positives, and false negatives, yields a score from 1 to +1. A value of 1 means perfect prediction, 0 indicates random performance, and 1 means total disagreement. MCC is particularly valuable in binary classification with severe class imbalance. In short, when working with imbalanced data, the real goal isn't just being right most of the time, it's being right when it truly matters. Selecting the right metric ensures your model's performance reflects reality, not just a convenient illusion. When traditional sampling and algorithm tweaks aren't enough, it's time to turn to advanced strategies. These methods are crafted for complex datasets, severe imbalance, or high-stakes scenarios where you need to go beyond conventional approaches. One such method is meta-learning, or learning to learn, which enables a model to dynamically adapt balancing strategies, like choosing between SMOT or class weighting on the fly. This provides automation and flexibility, especially when data distributions shift over time. However, meta-learning is computationally demanding and often difficult to interpret. It's well suited for multitask learning, continual learning, and low data regimes, and although applicable to any data type, it's most explored in image-based and few-shot learning domains. Another powerful approach is GAN-based oversampling. Generative adversarial networks, GANs, can create realistic synthetic examples of the minority class, making them ideal for complex data types like images or time series. The main benefit is their ability to produce diverse and high-fidelity samples, a big upgrade from traditional oversampling. Still, GANs are notoriously difficult to train and often require a substantial amount of minority data to get started. This limits their use in extreme imbalance scenarios. When feasible, GANs shine in applications like medical imaging, visual classification, and generative modeling across image, text, and time series domains. Inspired by the human learning process, curriculum learning offers another creative path. It introduces the model to easier, cleaner examples first, gradually escalating to more difficult or noisy data. This staged exposure helps the model gain confidence and stability before tackling ambiguous cases. While promising, this method hinges on defining what's considered easy versus hard, which can be subjective or complex. It's especially useful in deep learning tasks with high-dimensional data and works well across domains like NLP, educational data mining, and staged classification tasks, as long as difficulty levels can be clearly ranked. Perhaps the most radical shift is one-class classification, which flips the problem on its head. Instead of modeling all classes, this approach trains only on the minority class and treats all other inputs as anomalies. It's extremely effective in domains with extreme imbalance, such as rare event detection or fraud cases, where modeling the majority class offers little value. The catch is that the minority class must be internally consistent. If it's too heterogeneous, the model may underperform. One-class classification is popular in anomaly detection, cybersecurity, and predictive maintenance, and can be applied across tabular, image, text, or signal data. These advanced approaches aren't always easy to implement. They demand greater computational resources, careful tuning, and deeper understanding of the data. But when applied correctly, they can dramatically elevate performance in imbalanced settings. Whether through adaptive learning, realistic synthesis, staged training, or anomaly-focused modeling, these methods provide the edge needed to move from models that simply survive to ones that thrive under pressure. Now that we've explored how to handle imbalanced data, it's time to ask the most important question: why does this matter in the real world? Class imbalance isn't just a technical inconvenience. It appears in high-stakes domains where wrong predictions can lead to serious consequences. Often, the minority class holds the most critical insights, and failing to detect it can cost lives, money, or reputation. Let's examine where class imbalance shows up in practice and why it must be handled with care. In fraud detection, most transactions are legitimate, while fraudulent ones typically make up less than 1%. In this case, Catching a few false positives is manageable, but missing real fraud can result in massive financial loss. That's why high recall, strong precision, and the use of anomaly detection techniques are so important in this domain. Similarly, in medical diagnosis, especially involving rare diseases, the data is naturally imbalanced, with most patients being healthy. Here, models must excel at identifying true positives while minimizing false alarms. This makes metrics like recall, F1 score, and cost-sensitive learning critical for deployment. In the business world, customer churn prediction is a key application of imbalanced data modeling. Only a small percentage of customers actually leave, but predicting churn before it happens can significantly boost retention strategies. Handling this imbalance effectively often involves oversampling, class weighting, and balanced ensemble methods to detect subtle, early signals of dissatisfaction. These approaches allow companies to intervene proactively and retain valuable customers. When it comes to rare event detection, such as machinery breakdowns, critical failures, or natural disasters, the stakes are even higher. These events are infrequent but highly consequential. Yet the training data includes only a few examples of such incidents. In these scenarios, techniques like one-class classification, temporal augmentation, and curriculum learning can help models recognize early warning signs even when examples are scarce. These tools allow the model to focus learning on what really matters. In spam filtering and cybersecurity, legitimate activity dominates datasets, but missing a single phishing attack or intrusion can be dangerous. High precision becomes essential, and using cost-sensitive or ensemble models offers better control over the trade-offs between false positives and false negatives. As we've seen across all these domains, class imbalance is not just a theoretical problem, it's a pressing issue in many real-world applications. The right combination of data handling, algorithm design, and evaluation metrics ensures that machine learning systems are not only accurate, but also reliable, practical, and ethical in the face of imbalance.